Welcome back to this course on nanostructured materials, synthesis, properties, self-assembly and applications. We have had 2 lectures in module 1 and today is the 7th lecture of module 2. In the previous lectures, we discussed the synthesis using CVD techniques, that is the chemical vapor deposition techniques, the physical vapor deposition techniques and MBE techniques, which is molecular beam epitaxy techniques. Today we will start on the synthesis of nanostructured materials based on some template methods. The template based synthesis, as the name suggests, is based on some form of a material which will form the template and on which the nanostructured material will be made. Once it is made, the template will be removed and only the nanostructured material will remain. Now, this is schematically shown in a scheme which all of you must have seen. You must have seen pottery or Chinese pottery specifically, where the finished material is of clay or something, but how is this shape taking place? You start with a template. This template in this case is made of wood or it can be made of a metal, and then in this case we put the clay onto this piece of wood and the clay fills all the holes and all the gaps within the piece of wood. And then once you bake it, and then you remove the piece of wood, what is left is this jar which is made only of the clay. So, this is precisely what you are going to do in a template method. You are going to use a template and put some material which is clay in this case. In our case, you may use any nanoparticle, any other material which can be a liquid which will form a shape. The shape is being given by the template. This piece of wood here will be given by some other template which will be in the form of small structures and which will ultimately, when we remove that template, you will get, in this case you get a large structure, you will get small structures which are dependent on the shape of the template. So, what can be these templates in the molecular regime, in the nanostructural regime? You can use many templates. For example, you can use cation exchange resins which have micropores, that means the size of the pores are micropores. You can use zeolites. All of you know zeolites are aluminosilicates. They have 3-dimensional structures. They may have channels within them, or different zeolites have different size of pores. So, depending on which zeolite you use, you can either make a small particle or you can make a columnar structure. You can also use silicate glasses as templates within which you can make a material which will have in itself some features which are left from the silicate glasses. You can use ion exchange technique. So, you have a template in which there is a particular ion in the material, and then you ion exchange with another ion, and now you get a new material with the same structure as the initial template material. So, because only one ion or one set of ions have been exchanged in this methodology. You can also use gas deposition on a shadow mask. The shadow mask here will act as the template, and then this ordering of the gas molecules on this mask will give you the structure that you basically need, and for that you have to design this shadow mask, because according to that the gas deposit will take place and the structure that you need will be formed. So, these are different classes of templates. We discussed cation exchange resins, where cations can be exchanged, zeolites, silicates, and then other ion exchange possibilities. So, there are different types of pores, density of pores possible with different types of template or different type of membrane which are going to act as templates. For example, if you have a polymer, mainly polycarbonates are used for this purpose, where you etch ion tracks, that means you use ions and bombard these polymers, and these ions leave tracks, and these tracks are of the order of 5 to 500 nanometers. These channels or ion tracks as we call, and the density of these pores are of the order of 10 to the power 11 per meter square, and these are randomly arranged pores. You can also have a mica, which is a naturally occurring inorganic material, it is a mineral, and this mica has layered structure, and in this mica you can make this kind of etching to yield channels of 1 to 500 nanometer size, in which again you can have random pores of the order of 10 to the power 10 or 10 to the power 11 pores per meter square. You can also use alumina, which is aluminum oxide Al2O3, and in this alumina you can make channels of the type of 10 to 500 nanometers, and which is the pore diameter, and again you have 10 to the power 11 to 10 to the power 13 pores, but now in this case you can have ordered pores. So, earlier we were talking of random pores, but in the case of alumina and as well as in the case of block copolymers, we can get ordered pores and higher density of ordered pores, and the channel widths will vary from 10 to 500 nanometers in the case of alumina and 10 to 20 nanometers in the case where you are using block copolymers. Basically, block copolymers have two types of polymers, one may be a hydrophobic, the other can be hydrophilic, and they form two types of polymers joined together form a block copolymer, and there also you can create this kind of ion channels of 10 to the power 10 to 20 nanometers thick, which will yield you ordered pores in which you can do synthesis leading to nanostructured materials which are precisely ordered, because the pores in which you are doing the synthesis are precisely ordered. So, you can have random pores or you can have ordered pores, and using these different types of membranes we can yield random nanostructures or ordered nanostructures. So, these are various types of membranes and templates which are used to grow nanowires within these pores. So, you can see you can generate from around 1 nanometer diameter to up till 500 nanometer diameter wires, and many wires you can generate of the order of 10 to the power 10 to 10 to the power 13, depending on which methodology you use to grow these nanowires in these templates. So, here you can see this is an example of a template mediated growth, where you are trying to grow carbon nanotubes on silicon nanowire tips. So, here the silicon nanowire is the template on which you are trying to grow carbon nanotube. So, the carbon nanotubes are these thin tubes which are growing out of these silicon nanowires. And so, the carbon nanotube is being guided by the silicon nanowire, which has been formed earlier. This is a close up view, where you can see this is the silicon, which has a wider or larger diameter, and on top of that you have this carbon nanotube. The scale here is around 10 nanometer. So, half of this is around 5 nanometer. So, you can think of this is like 5 to 7 nanometer thick carbon nanotube grown on around 15 nanometer thick or 20 nanometer thick silicon nanowires. So, these are very useful techniques. The template based techniques are very useful to prepare nanowires, which are precisely ordered in a particular fashion. To look at these carbon nanotubes more carefully, here is a high resolution transmission electron micrograph. So, you have to use an electron microscope, which has working under a voltage of around 200 to 300 kilovolts, and accelerated electrons come and hit the sample, which is loaded on a grid, which may be a copper grid or something, and the electrons then make an image of the particles that they see, and depending on the voltage, the wavelength of the electron can be modulated, and the wavelength of the electron can be of the order of 0.05 or 0.02 angstroms, and so you can see objects which are very, very small. And so, here is a carbon nanotube, and you can see the different layers of carbon, and this is a typical thickness between the walls of two carbon layers of around 3.4 angstrom or 0.34 nanometers. And in this slide, what you see is that you have this silicon nanowire, and on the tip of the silicon nanowire you have this carbon which is growing on top of the silicon nanowire. So, the silicon nanowire is acting as the template, and on top of that you have this carbon rather than a nanotube, here is like more spherical. And so, these spheres of carbon, since there are several layers in each sphere, this is called a onion like structure, and so these are called carbon nano onions. It is nano because they are of the order of few nanometers in diameter. So, this is 0.45 nanometers. So, around this whole thing may be around 10 nanometers or 8 nanometers, right. So, here we are seeing silicon nanowire, which earlier we showed this is silicon nanowire where carbon nanotube is growing, and here we are showing silicon nanowire as a template. At the tip of that, carbon onions are growing. Now, you can have several other kinds of hosts. So, we discussed you can have 1D tunnel hosts like zeolites, which have tunnels like this or channels, or you can have lipid bilayer vesicles or many other inorganic compounds which have tunnel structures. So, you have vacant spaces between the cylinders in which you can grow nanowires. You can also have hosts which are two dimensional in nature, and these are layered hosts which can be made of materials which are layered materials like molybdenum dioxide or LiNBO2 or lithium cobalt oxide. These can be oxides, these can be halides or chalcogenide layers, for example, molybdenum disulfide, tungsten disulfide, molybdenum diselenide. These are all two dimensional layered materials. In between the layers you can grow your material which you want to grow, and this layered, the blue colored layers will then act as a template, and after the reaction you have to remove these templates to regain the material which are in between the layers. So, here you get one dimensional linear structures when you make materials within the cylinders. Here you get two dimensional structures which when you make the synthesis using these 2D layered hosts, and this is a 3D layered host. So, they form porous structures. So, there are pores inside. So, this is a 3D framework host, and many materials have zeolites can have this kind of cylindrical pores. They can also have this kind of 3D pores, which are of the order of 4 to 10 to 20 angstroms, few nanometers, and you can have many other polymers, buckyballs, etc., as 3D framework hosts, where you can generate only particles and not layers, and you cannot generate wires. Normally, you will generate particles when you use 3D hosts as templates for your synthesis, whereas here you can generate wires, and in this case you can generate 2D layers using these particular hosts. This is another method where you are going to make metal nanostructures using a template based synthesis. So, you have say gold one metal here and aluminum another metal here, and then you make many structures to separate the layers which will form in between, right, and these you fill with a copper solution, right. So, there will be copper solution here, which and in between you have membranes. So, what happens depending on the redox potentials, the metal that you have chosen, aluminum and copper will get reduced easily. So, it will accept electrons to form this copper solution, which may be copper nitrate solution or copper sulphate solution. You will have copper ions in this solution, and it will readily take up electrons which are given by any metal. So, the metal which will give up electrons easily are this aluminum metal, and this aluminum metal, when it gives out electrons, it forms aluminum ions and goes into solution, and the electrons that it gives out, that is actually coming in here, reacting with the solution, and copper 2 plus gets reduced to metallic copper, and wherever it gets reduced, it gets deposited. So, this wherever copper 2 ions are there, they get reduced and they form copper metal layers in these cavities. So, now you have a particular order of copper metal which are separated from each other by this gap, because no copper metal can deposit here, which are the membranes, and only the gap which is available where the solution can go can be reduced to copper metal. So, you will have copper metal regularly spaced between this region, and then again you will have copper here, and again you will have copper here, like that. So, you can arrange systematically using this template, and here we call this the anodized aluminum. So, aluminum is the anode and it is acting as an anode, and so this aluminum metal template is also called the anodized aluminum metal template, which is used for doing the template based synthesis for metal nanostructures. And it is possible to make nanostructures of those metals which have a much more ease in accepting electrons from aluminum. So, they have a higher reduction potential compared to aluminum. Now, what other materials can you make using these template based methods? You can make inorganic materials, you can make organic materials. Inorganic materials like metals, like just now we showed copper metal, we can make gold, silver, we can make organic compounds, we can make polymers or metal organic compounds, like you suppose you have to make a compound of palladium with some organic moiety, which may be a pyridine based or naphthalene based, etc. So, you can make materials of different kinds using the template based synthesis. You can, these materials that you are depositing using the help of a template, they may have a wide ranging properties. Some can be insulating, some can be semiconductors or metals or even superconductors, that is those in which the resistance below a certain temperature goes to 0. Such kind of materials are called superconductors, and so you can deposit any kind of material if you choose the right conditions, the right template and the right reaction, whether it is a reduction or some other reaction. So, you can make a wide variety of materials with different properties, and the size of these can vary. If you have channels, that is one dimensional channels, you can have diameters from 5 to around 10,000 angstroms of these materials. So, you can have wires which are from 5 angstroms to around 10,000 angstroms. So, which is like 0.5 nanometers to around 1000 nanometers, or which is 1 micron. So, you can have from 0.5 nanometers to 1 micron sized linear arrays of nanostructured materials using templates. If you want to make 2D structures within the interlamellar spaces, so these are the interlamellar space. So, between this one blue layer and another blue layer, this space is called the interlamellar space, and your material that you will be synthesizing using this 2D template or this 2D host will be synthesized within these 2 dimensional layers. So, which is also called the interlamellar space. So, in the interlamellar space you can make layers which are of the order of 3 angstroms wide or 3 angstroms long up till 50 angstroms wide and 50 angstroms long. That so, a very large, like micron sized nanostructures are possible in channels, but normally in the interlamellar spaces or 2D structures it is difficult to make very large layers of 2D structures. In the cavity diameters, there is a 3D structures where you have cavities like this. Here also you can make vary the cavity size depending on the choice of your carbon sieves or the zeolites or the polymers, what kind of cage you have. You can have variety of sizes, and hence you can make a very large cavity diameters. Typically they are on the larger side, and it is very difficult to get very small 3D structures. So, depending on the shape of the material, you have some restrictions on the type of size you will get, and in 1D structures you can get very large values, and in again 3D structures you can get very large values. However, for 2D structures or 2D nanostructures made within the interlamellar spaces of the template, you normally get sizes which are of the order of 3 to 50 angstroms. Now, you can also use surfactants as a template. So far we were discussing zeolites or metal oxides or metal chalcogenides, 3 dimensional structures, 2 dimensional structures which are like inorganic, hard inorganic solids, whereas here you can make aggregates of surfactants, and these aggregates form from molecules which normally have a organic long tail with some kind of a ion at the head. So, it is these surfactants are made of a head group which can be like an ammonium group or any other head group with say tri-alkyl group with the nitrogen, which may be charged or it can be uncharged moiety, and most of the time the head group is polar, much more polar than the tail group. So, the tail and the head together form a molecule which is called a surfactant, and these surfactants can organize themselves to form spherical micelles, or they can form cylindrical micelles, or they can form two micelles, one inside and one outside, and then there is a gap in between which goes throughout the sphere, and this kind of aggregates of surfactants are called vesicles. So, you can make use of these as templates and synthesize your material within this cylinder or within this sphere or within this what is called a bicontinuous structure. So, depending on the type of surfactant, its concentration and the solvent in which it is present, you can have different kinds of structures, and you can then synthesize a new material within these structures. So, the surfactant now acts as a template within which you make your material, but it will be shaped like the template. So, if you use the cylindrical micelle and do the synthesis inside the micelle, then the shape of the product that you will get will also have a shape like a cylinder. So, it will do what is called the templating effect. Now, you can choose a wide variety of surfactants, and so there is lot of choice how to control the diameter of this cylinder, how to control the length of the cylinder, how to control the diameter of this spherical micelle, etc. So, surfactants are a very rich source of templates if you can make them aggregate the way you want them to aggregate or the way you want your final structure to be, because ultimately you have to remove this template and the remaining structure should be the final structure what you want with your material left behind. So, this is an example where you have these surfactant molecules, and these surfactant molecules can be organized. So, they are organizing and forming a cylinder, okay. And this cylinder in that cylinder you can synthesize something within this cylindrical space, and then you remove the outside cylinder to give you the material that you want in the shape of a cylinder. So, this is the templating effect. So, this is aggregation of the surfactant molecules to form the template which looks like a cylinder. Then you, the B step, you add or form your desired materials within this cylinder after the stage B. And after the stage C, you remove whatever is outside and you are left behind with the material which you have made inside this aggregated surfactant molecular structure. So, this kind of a cylindrical micellar structure ultimately yields a nanowire if the dimension of this wire, the diameter is in nanometers, and most of the time you can get nanowires of 5-10 nanometers, and lengths you can vary from 100 nanometers to few microns very easily. In this step you have to remove the surfactant molecules to get, either you use appropriate solvent to remove the surfactants, or you can heat this material. So, the surfactant molecules will all go away and you are left with the nanowire. So, this is a template based synthesis using surfactant aggregates to form nanowires. This is another example where you use these kind of surfactant molecules which are also called amphiphilic molecules. That means, they have two properties, one hydrophobic and hydrophilic, both are there in the same molecule. There are two parts, and here we are discussing the synthesis of gold nanoparticles in micelles, and these micelles are made like, as we said, this is a cylindrical micelle made from surfactant molecules. So, in this case also you have micelles, but of course, in this case these are spherical micelles, and these spherical micelles are made up by some kind, as you see, two structures, one thin tail and one solid rod, and this kind of a polymeric structure is called a block copolymer. So, you have two parts to the polymer. So, one part of the polymer which itself is a polymer is probably hydrophobic, and the other part of the polymer is another polymer made of more hydrophilic nature, and the two parts are joined together. So, this is called a block copolymer, and when these block copolymers arrange themselves like surfactant molecules at a particular concentration to form a micelle, with all the parts of the block copolymer which are alike have come together, and those which are different are also close to each other, but away from these structures. So, when you have this organization of a block copolymer to form a micelle, then you add your metal salt from which you want to make your metal. In this case it is gold particles. So, you have to add gold salt, and this gold salt attaches to one part of the polymer which it likes. So, it attaches to say the more polar part of the block copolymer. So, all the dots as you see are attached to the more polar part of the block copolymer, and then you can do a reduction or treating the core such that you get the nanoparticle at the center, and that is explained more clearly in the next slide, where we discuss. So, what we were discussing is an AB diblock copolymer which is first used to form a micelle using the surfactant like behavior of aggregation, where like form the polar head groups in surfactants come together to form a micelle, and the tails are pointing outwards. In this case the block copolymer has two parts, a polystyrene part and a 2-vinyl pyridine part. So, the styrene part and 2-vinyl pyridine have different hydrophobicities, and so one of the parts, the 2-vinyl pyridine, which is more polar, that forms the head group and arranges close to itself, and when you add chloroauric acid, which is the starting material to make gold nanoparticles, this chloroauric acid, when you add to this solution of block copolymer, binds selectively to this vinyl pyridine based polymer, and that is the vinyl pyridine part of the polymer is here, and so that is where the gold nanoparticles will the salt of the gold nanoparticle gets attached, and then it is solubilized and then transformed to the metal by reduction. So, when you use a chemical reaction to reduce the gold ions to the metal. So, in this step you finally end up with the gold particle at the center and the block copolymer around it. So, this is a typical synthesis of using a diblock copolymer as a template to make gold nanoparticles. The diblock copolymer appears to function like a surfactant does and forms a micelle, and the auric chloride attaches to the head group and then can be reduced to form the gold nanoparticles at the center of the micelle. Now, another template that people use quite often are what are called nucleopore membranes, nucleopore filters. Basically, it is a filter made of a plastic or a polymer, usually polycarbonate, and which has got holes on it which are few microns in diameter. So, this is typically a nucleopore membrane and can be used as a nucleopore filter. So, how do you create these holes? You expose the membrane to radiation, and that radiation weakens the plastic, and then you add certain chemicals or acid which can remove or make holes in those specific areas which are weakened by the radiation. So, first you weaken the plastic at certain positions depending on the design which you want, where do you want the holes to be created of micron size or submicron size, and then once you expose them to radiation in a patterned manner, then you expose them to some chemicals, and the weakened part of the plastic or the polymer which is patterned then will generate these holes which can be used as a nucleopore filter. So, these nucleopore membranes or filter can be used, or people have used, to synthesize compounds within those pores like polypyrrole, poly-3-methylthiophene, and a nanoporous nucleopore membrane was used. That means, the holes which were made were of the diameter of few nanometers, and then this membrane, which is basically a polycarbonate which was treated to some rays or radiation, and then it was some acid or other chemicals were used to make holes, and then that porous nanoporous membrane was used as a template, and this had cylindrical pores of the order of 300 angstroms to 10,000 angstroms in diameter, which is 1 micron. So, from some 30 nanometers to 1 micron, that is the diameter of the pores that you can create in these nucleopore membranes, and they are linear cylindrical pores, very much like the case that we discussed earlier. These can be considered linear cylindrical pores, and if these diameters what we see in the nucleopore membranes, this diameter will be around 30 nanometers to about 1 micron. Okay. But they were created from one sheet. In this case there are different cylinders, but in the nucleopore membrane there was one full sheet, and then holes were made by selectively exposing to radiation at certain spots, and then those weak spots were then made into holes by chemical treatment. So, that is the nucleopore filter which you can start from a polymer membrane like a polycarbonate membrane, and where you can get cylindrical pores of the size of 13 nanometers to 1 micron, and the monomer solution is separated by the polymerization agent by these membranes. So, before polymerizing, you have only the monomer solution and you have this membrane, and once you add the polymerizing agent, then the nucleopore membranes will be in these pores. You will have this polymerization taking place, and you can make compounds like polypyrrole, and poly-3-methylthiophene has been shown to be made in these porous membranes, which are basically made of polycarbonate films with holes drilled in them, not by any drilling machine, but using some radiation and then chemically treating them to make porous cylindrical type of structures, in which by doing reactions with monomers you can polymerize and get nanostructures, polymeric nanostructures. Now, you can also use biomaterials for templating. So far we have discussed inorganic materials, organic materials which are polymeric materials. You can also use biomaterials for templating. In general, we can call them as biotemplates. Some of the examples of such biotemplates can be, for example, a bacterial cell surface protein. So, on the surface of a bacterial cell there are several proteins, and these proteins will have some structure which will control the formation of other materials if these are used as templates. You can have small sized nucleic acid compounds which are of the size of nano and micrometer, and they can be thought of or they can be used as templates during the formation of other materials. You can have hollow compartmental like structures in viruses, and then you can use those viruses as biotemplates. So, there are cases where hollow biomolecular compartments in like viruses have been used to synthesize materials within the viruses. So, that is another example of biotemplating. Then we can we come across a term which is called S layers. Basically, from single polypeptides, if you can make many copies, multiple copies of a single polypeptide, then it can form spontaneously highly regular nanoporous lattices. So, you have a polypeptide chain, and that polypeptide chain spontaneously aggregates to form regular superlattices, that is they are ordered in space over a large dimension, and this can be of various symmetries. So, there can be rectangular symmetry, hexagonal patterns of these polypeptides which arrange themselves. So, one single polypeptide makes multiple copies of that, which spontaneously aggregates in some patterned form, and then leaves behind or leaves along with it some nanopores like this, and then you can do synthesis in these nanopores, which are having as the template these polypeptide chains, many numbers of polypeptide chains starting from a single polypeptide. So, in this, if you do synthesis, then it will be called biotemplating, because your template is a biomolecule, it is a polypeptide chain, and hence these are different examples of biotemplating. So, typically you make an S layer, that means you make a layer made up of this polypeptide chain which organizes itself. So, it forms say a pattern, and this pattern is we are showing in one dimension, but it can be like this in 2 dimensions, right. And here what we are showing schematically is that these S layer, which is organized as a pattern, is on a TEM grid, because we want to use the TEM, and so you make this pattern on the TEM grid. So, once it is on the TEM grid, then you coat this S layer with gold. So, suppose you are able to coat these S layers with gold, because they are these biomolecules are functionalized, and you can have thiol groups, and to the thiol groups you can attach gold. So, suppose you can coat gold on these surfaces. So, all your entire pattern now is covered with gold, but then you want gold in the centers, you want it to be patterned at the center. So, what you do is you can pass electron beam, which is shown here, the electron radiation, and all the gold from here then enters into the cavities in between the gaps between these 2 ordered subunits of the polypeptide chain or the S layer. So, you can have gold particles in these gaps which have like kind of melted and reunited to form droplets on being exposed to an electron beam. So, this is an example of biotemplating. So, you have a S layer pattern based with single polypeptide chains, and you have gold coating on top of them, then you irradiate with electron, and all these gold forms droplets, and they are arranged regularly because this spacing is fixed, and so you can have now a regular pattern of gold nanoparticles made using a biotemplated route. Then you can use magnetotactic bacteria as a biotemplate. What is this magnetotactic bacteria? These are bacteria which are found mainly in the sea, and the word magnetotactic tells you that they have some magnetic property associated with them. So, these are in biology, this is a group of prokaryotes, and they are especially interesting since they orient and migrate along with the Earth's magnetic fields, which is called the geomagnetic field lines. So, that means the bacteria can find out where is the Earth's north pole and the Earth's south pole. So, the magnetic lines of force of the Earth, the bacteria can find out. So, how can it find out? That is because it has got some magnetic particles inside the body. So, this migration of these bacteria based on the Earth's geomagnetism is related to the magnetic structure or the magnetosomes inside these bacteria, and these magnetosomes are nothing but ferric oxide Fe3O4 particles, which are also called magnetite particles, which are bound inside the membrane of these cells, okay, and these are called magnetosomes. So, to explain to you what is a magnetosome or how this happens is, if you consider this to be a cell. So, there is an outer membrane of the cell and there is a cytoplasmic membrane, inside you have the cytoplasm. So, it is known that inside the cytoplasm there are these magnetosomes. So, these are these magnetosomes, and inside the magnetosome you have this Fe3O4, which is magnetic in nature. It will be attracted or interact with magnetic field, and this kind of particles are present within the cell of the bacteria, of the magnetotactic bacteria, and that helps it to guide, to move the bacteria based on the magnetic field of the Earth. Now, this Fe3O4 particle is covered with a membrane which is called the magnetosome membrane. So, here what we show is how does this Fe3O4 form inside the cell. So, what is known today is that the Fe3 plus ions from outside the cell. So, it is in the solution which is outside and can come in through this cell membrane and form Fe2 plus, but the exact mechanism is not known how Fe3 plus comes within the cell wall. From Fe2 plus within the cell, it enters this magnetosome. So, we have pictured the magnetosome like this, where once it comes inside you get ferric oxide which is hydrated. So, all this iron is Fe3 plus, right, and here Fe2 plus is there. So, they together Fe3 plus and Fe2 plus give you Fe3O4. So, ultimately you get a particle which has got Fe3O4 inside, outside there is a membrane, and the whole thing is called a magnetosome. And so, this magnetosome with Fe3O4 inside the cell, many of these are there, and they control the movement of the bacteria in the presence of a magnetic field, and how the formation, exact formation, how does the ions move inside are still certain questions, but lot of it depends on the pH and other redox behavior in these magnetotactic bacteria. This is a real TM pictures of these bacteria. So, you can see these particles, magnetosomes with the magnetic particles, they align themselves in some particular direction inside the cell, and this direction is guided by the Earth's magnetic field. So, you can find many different types of shapes of these magnetosomes. They can be little bit hexagonal like here, or they can be like cuboids, and the most important thing is most of the time they will be aligned in a certain manner, and this alignment is important for the bacteria to navigate in the sea based on the Earth's magnetic field. So, this is an example of biotemplates, where the cell is the template, the magnetosome is the template inside which the bacteria is forming inorganic materials. Fe3O4 is an inorganic material, which the formation of that is guided by the structure of the magnetosomes. Now, next after this we will come to the next lecture, which is on template methods again, part 2, which we will continue in our next lecture, which will be the lecture 8 of module 2. So, thank you.